The recent research focuses on two questions that one could raise about DQE. So first one is how to make the ansatz exact. And the second is how to make the classical optimization process easier. I will also discuss that when running a VQE on a noisy quantum device, such as a real quantum hardware or a simulator with a noise model, what we can do to reduce the error. Okay, so let's start today's lecture by doing a recap on VQE algorithm. So the VQE implements a parameterized wave function ansatz on a quantum computer. It then repeatedly measures and optimizes the energy expectation value, the second step of this ansatz, until the optimal parameter set is found. So different ansatzes could be implemented in VQE. The most straightforward one is a unitary coupled cluster ansatz with singles and doubles. The UCCSD is motivated by the failure of the traditional CCSD in the description of strongly correlative systems. We have also discussed the hardware efficient ansatz that has gained a lot of attention in recent years. Compared with UCCSD, the hardware efficient ansatz is easier to implement on a quantum computer, but its performance is harder to analyze. So compared with the quantum phase estimation algorithm, the main disadvantage of VQE is that it is an approximate wave function. Therefore, it's hard to tell how well or how bad it will perform for given systems without any prior knowledge. Moreover, it will also require classical optimization techniques for the multivariable nonlinear function, which could be very difficult, especially for noisy quantum devices. Okay, so let's address the first problem of VQE, namely, how do we make it an exact method? One of the first ideas is from the UPCCGSD ansatz. Recall that the unitary coupled cluster ansatz is defined in the top equation by acting this exponential t minus t dagger onto the Hartree-Fock reference state. The KUPCCGSD generalizes the UCCSD ansatz by acting not just one, but k of the exponential of t minus t dagger onto the Hartree-Fock state. Each set of the t operator has its own parameter set. However, it is important to note that the t operator in the KUPCCGSD is not the same as in UCCSD. In UCCSD, we include all the possible singles and doubles excitations from occupied Hartree-Fock orbitals to unoccupied Hartree-Fock orbitals. In KUPCCGSD, firstly, we do not only include single excitations, like like schematic picture shows here, we also include single D excitations. For the double excitations, the UPCCGSD only allows for pair excitations, shown here. Namely, it does not break the alpha-beta electron pair. So if this K is 1, then the KUPCCGSD ansatz becomes a simplified version of the UCCSD ansatz. And if K is larger than 1, then the KUPCCGSD ansatz could be more flexible than the UCCSD ansatz. Here shows the energy error versus the full configuration interaction energy predicted by the KUPCCGSD ansatz, with K being 1, 2, and 3 for the water molecule. As you could see here, if K is 1, shown by this green curve, like the UPCCGSD yields large amount of errors in the stress region, and its accuracy is much worse compared to the UCCSD ansatz. However, the amount of error becomes smaller and smaller as one increases G. Here for K, as one increases K. Here for K being 3, you can see that's for this dashed line, the error becomes basically negligible. So the success of the KUPCCGSD ansatz inspires people to think about the exactness of the UCCSD ansatz. Consider this ansatz showing the top equation. This is the disentangled unitary coupled cluster ansatz. The DUCC ansatz is defined by acting a product of the exponential of the sigma operator onto the Hartree-Fock state. And the sigma operator is just a t minus t dagger, in which t is a general operator, such as one body, two body, and three body operators. And one could prove that if t includes all the possible operators defined by the system size, and one applies these operators in a special order, the DUCC ansatz becomes exact. So with this proof, we could decompose all the higher order operators into one and two body operators, For example, shown here, the three-body operator could be decomposed as a summation of commutators of two-body operators. Similarly for other high-order operators. And then the exponential of this commutator of A and B could be further decomposed as an infinite product of the exponential of A and B. With these two steps of decomposition, we basically prove that the DUCCSD, like this DUCCSD infinite ansatz, in which one applies infinite number of exponential of one and two body operators, is an exact ansatz. So although in reality, we could only apply finite number of these operators, this proof does provide a way to achieve arbitrary level of accuracy for the UCCSD ansatz, which is just to keep applying the exponential of one and two body operators to the Hartree-Fock state. However, is there a clever way to choose which one and two body operators we want to apply so that we achieve the highest efficiency? So it turns out that there is a way of doing this. This is the adapt VQE approach. Firstly, it defines a pool of all the one and two body operators. As usual, we initialize our wave function in the Hartree-Fock state. And then we select a subset of the operators in the pool by random sampling, for example. The ansatz is now defined by acting these selected operators to the current state, which is the Hartree-Fock state. And the next thing, which is very important here, is to measure the energy gradient with respect to every parameters associated with every operators. The gradients are nothing but the expectation value of the commutator between the Hamiltonian and the operator. And if the gradients are below some small threshold, then we consider the optimization has been converged. If not, we select the operator with the largest gradients and then grow the ansatz by applying this operator to the current ansatz. This choice makes sure that the operator we add is most likely to reduce energy by the largest amount. We then optimize the parameters for this new growth wave function and then go to the operator selection step. So as one could see that by varying the convergence threshold epsilon of the adapt VQE method, we could basically achieve arbitrary level of accuracy. In reality, one needs to balance the cost and accuracy to find the most optimal threshold. Here are the three examples of potential energy surface predicted by the adapt VQE algorithm, comparing with full CI results and the UCCSD results. People explore three different epsilons, with epsilon 1 being the largest one and epsilon 3 being the smallest one. And we found the accuracy of the adapt VQE increases as epsilon decreases for both the beryllium hydride, shown by the second example, and the H6 chain. We also find that the accuracy of the adapt VQE algorithm with epsilon 2 and epsilon 3 surpasses that of the UCCSD ansatz. Okay, so a similar method as the adapt VQE algorithm is the qubit couple cluster method. Unlike either of UCCSD or adapt VQE, which start in the fermion space and then transform it into the qubit space with, for example, the Jordan-Wigner transformation. The qubit couple cluster method works in the qubit space directly. Its wave function is defined by the entangler acting on the mean field state. The mean field state is a product of single qubit states parameterized by the parameter theta and the parameter phi. The entangler is a product of the exponential of minus I times a Pauli word. A Pauli word is just a tensor product of Pauli matrices. So in general, there are 4 to the n cubed number of possible Pauli strings, and it's certainly impractical to implement all of these Pauli strings in the ansatz. The qubit couple cluster applies a similar idea as in the adapt VQE algorithm, which is to rank the entanglers first based on their importance to reduce energy and only select the high-ranked entanglers. So let's first define the mean field energy, which is energy for the big omega wave function, the unentangled wave function, with optimal parameters theta and phi without any entanglers. Now suppose we add one entangler to the wave function associated with the Pauli string P of k. Its energy is computed with the second equation here. We could then compute the energy derivative with respect to the parameter tau, which is just an expectation value of the commutator between the Hamiltonian and this polystring P of k with the mean field wave function. We then rank the entanglers based on the energy derivatives and only include entanglers whose energy derivative is larger than a pre-chosen threshold in the overall wave function. And on the right here shows the performance of the cubic couple cluster wave function for the lithium hydride molecule, comparing the cubic couple cluster, the mean field, no entangler wave function, and the exact one. As you can see, that although the mean field wave function, as expected, performs quite poorly, but once we add entanglers to it, the cubic couple cluster and energy matches the exact energy perfectly. So earlier this year, there is a paper published on the Physical Review Letters in which the author developed a novel solver for the quantum contracted eigenvalue equation, which I find to be very interesting. First, let's recall the Schrodinger's equation, shown by the first top equation here. We then left multiply the Schrodinger's equation by this particular term, and then perform some mathematical tricks. We will then obtain the anti-Hermitian part of the contracted Schrodinger's equation, the ACSE equation. It has been shown that the solution to the ACSE equation is equivalent to the solution of the original Schrodinger's equation. So now solving the Schrodinger's equation becomes equivalent to solving the ACSE equation. So in order to solve the ACSE equation, we iteratively grow a variational wave function on those. In the n+1 iteration, for example, the new wave function psi n+1 is obtained by applying the exponential of the scalar epsilon multiplied by the anti-Hermitian two electron operator A to the current wave function psi n. If we expand the energy and the energy gradients with respect to A using the Taylor series in terms of the parameter epsilon, it results in these two equations in the bottom. Interestingly, we find that the residue of the ACSE equation is actually the negative of the energy gradient with respect to A. So now at the n+1 iteration, one needs to grow the ansatz. So the question becomes how to choose the parameter A and the parameter epsilon. Since we know the energy gradient with respect to A, we could simply set A to be the negative of the energy gradients, which is the same as the residue of the ACSE equation, which is a second step here. And this is equivalent of doing a gradient descent optimization. And this is what the step 2 is doing. It prepares two auxiliary wave function with the parameter delta, and then compute A using the finite difference algorithm. And then the two terms in the finite difference algorithm these two terms in the finite difference algorithm could then be measured on a quantum computer to compute A. So once A is decided, what's left is to decide the parameter epsilon, which is equivalent to the learning rate in machine learning context. What we could do is just to compute the energy with different epsilon value and pick the epsilon that results in the lowest energy. Once both A and epsilon are decided, we grow the ansatz according to these parameters, and then we go to the next iteration. So let's now look at the performance of the ACSE solver. On the left is the energy convergence with respect to the number of iterations, and on the right is a predicted potential energy surface for the hydrogen molecule. Here we compare the exact energy, the simulator with no noise, and the real quantum device. As you could see, for a noise-free simulator with less than 10 iterations, the energy has been converged to the exact energy. And a similar behavior is also observed for experiments on a real device, as shown by this blue curve. Although the noise makes it convert to a much higher value compared to the noise-free simulator. So as you could see by now, the performance of the VQE algorithm, whichever version you use, either the adaptive VQE or the ACSE, the performance of these VQE algorithms on real quantum computers depends on the noise of the system. Without error corrections, algorithms that provide exact answers on a noise-free simulator result in significant amounts of errors on a real quantum computer. Therefore, we need to find a way to correct the errors in the VQE algorithm. So one way to do the error correction is to perform some checks for certain known physical quantities. One example would be the total number parity check. Now consider a 2-electron 4-orbital problem. One electron is spin up and another electron is spin down. On the left are some allowed measurements. For example, the first one is to have the first and the third orbital being occupied and the second and the fourth orbital being unoccupied. And this bit string has parity of 0, since we have even number of electrons in the system. On the right here are actually some unphysical measurements because they are wrong of the total number of the total electron number. For example, the first one has only 1 electron, and the second one has 3 electrons. And these measurements have parity being 1, since they are odd number of electrons there. So based on this observation, we could use an ancilla qubit to compute and store the parity with a circuit on the bottom. This could be done with two CNOT gates. For example, if both x0 and x1 are 1, and then the ancilla qubit will be flipped twice and end up in the 0 state, indicating a 0 parity of the system. We could then measure all 3 qubits, and if the ancilla qubit measurement is 0, we keep this measurement. And if the ancilla qubit measurement is 1, and then it indicates an error has happened, and then we discard the measurements. The check for the total parity, total particle number parity could detect errors in which the 2 qubits are incorrectly flipped, in which the 1 qubits are incorrectly flipped. For example, but it cannot really detect errors in which 2 qubits are incorrectly flipped. For example, consider like the all 0 state. This is a state with no electrons, but has a parity of 0, which is the correct total number, particle number parity. In order to detect these kind of errors, what one could do is to check the parity for both spin up and spin down electrons individually. Again, this could be done with an ancilla qubits with 2 measurements. And if both measurements results in 1, and then we keep the measurements. And if any of these measurements results in 0, this indicates an error has happened, and then we discard the measurements. So besides the error detection, another way to perform error correction is through error extrapolation. This is a method developed by IBM. The idea is to rise energy on a noisy quantum device, with error rate being lambda at the top equation here. So epsilon E star is the energy one obtains if no error has occurred, and the rest of the term is a polynomial in terms of the error rate lambda. The idea of the error extrapolation is to control the error rate. For example, suppose lambda is the smallest error rate one could get, and then experimentalists could enlarge the error rate, for example, by a factor of 2 by changing the lasers, for example. By doing so, one could obtain a few energy measurements that correspond to different error rates. And then we could do an extrapolation to zero error rates. So on the right are some results using this error extrapolation techniques. The green, yellow, and the red dots, for example, if you look at this plot, correspond to the noisy experimental results with different error rates. And they are actually pretty far from the exact results shown by this blue curve. However, after you perform the error extrapolation, the extrapolated results showing by the blue dot actually match nicely with the exact energy. And then the error detection and the error extrapolation techniques shown by the last few slides could then be combined. On the left here is a plot that shows the energy error versus the 2 qubit error rate, comparing the raw experimental data, error detection if one and the results if one performed error detection alone, the results if one perform error extrapolation alone, and the results with a combination of the error detection and error extrapolation. And you can see if the error rate is larger than 0.5%, then neither of the error detection or the error extrapolation alone yields chemical accuracy results. Once these two techniques are combined, then the chemical accuracy result could be achieved even with error rates as large as 1%, which is achievable on near-term devices. So in the end, I would like to talk about the neural error mitigation method that has been published recently. From my perspective, this is not actually an error mitigation method. The quantum algorithm here merely acts as an initialization state for the classical simulation. For the neural error mitigation techniques, the first step is still to optimize the VQE algorithm and obtain the results on a noisy quantum device. So once we have obtained this noisy quantum state optimized by with the VQE algorithm, we can then sample from the VQE wave function to form a dataset D. And from this dataset, we build a neural network that is capable of reconstructing the quantum state on a classical computer. And then we can then further optimize the neural network and obtain the results on the final optimized wave function. The major problem with this approach is that in the end, it is a classical simulation. The accuracy of the wave function is limited by the flexibility of the neural network. Also, using quantum computing as an initialization step may be able to accelerate the classical optimization process. All right, so in this lecture, we have discussed some of the recent research in variational quantum eigensolver and quantum error correction techniques. These research are trying to tackle two major drawbacks of the variational quantum eigensolver approach: its approximate nature and the requirement for classical optimization. So the adapt VQE and the cubic coupled cluster method grows the ansatz iteratively based on the importance of the excitation operators in adapt VQE and the rankings of the entangles in cubic coupled cluster. The adaptive VQE is proved to be capable of reaching arbitrary level of accuracy. The quantum anti-Hermitian contracted Schrodinger's equation, quantum ACSE, provides another way for growing the ansatz with two-body density matrices. Its advantage is that it does not require one to perform a multi-dimensional optimization process as in the adaptive VQE algorithm. And finally, we find that the accuracy of VQE algorithm on a real quantum device depends on the error rate. Both error detection and error extrapolation have been developed to reduce error, and they could be combined further to reach even higher accuracy. So this ends our quantum chemistry lecture series. During the last 4 lectures, we have discussed the quantum chemistry problem, the quantum phase estimation, the variational quantum eigensolver, and techniques used to reduce the computational cost and correct errors. However, this is nowhere near a comprehensive review of quantum algorithms for quantum chemistry problems, as many methods are still being developed on a daily basis, and quantum chemistry is perhaps one of the most difficult problems for quantum computing. So going forward, the success of simulating quantum chemistry problems depend both on the development of hardware and the development of softwares. For the hardware, we need to continue to bring the error rate down and build quantum computers with more qubits. For the software, we need to develop efficient methods that could reduce the amount of resources needed, along with error detection and error correction techniques. With rapid developments on both sides, I think the future for quantum chemistry simulation on quantum computers is bright, and the benefit we got once we reach quantum advantage will be tremendous. I hope you share the same view as me and all learn something from the lectures. Okay, so before we do the hands-on section, I will answer any questions you might have.
I have a question about the DU-CCSD. I mean, decoupled CCSD.
The de-entangled.
Oh yeah, yes. So you say that the operations should be selected randomly, but I don't understand why it should be chosen with random selection.
Well, so one thing, one thing you can do is just to compute like the energy gradient of all of these operators, and then do like a sorting or ranking to find like the ones with the largest energy gradients. Random sampling is something you can also do. For example, if you don't want to compute all of the operator, if you don't want to compute the gradients for all the operators at once, we can just randomly select some like subset of it, and then add and then compute the gradients, and then grow your ansatz, and then you can do it for many iterations. Essentially, I think you will be able to reach the same results. No, it doesn't really matter whether you do it randomly or do it deterministically. Just one choice is do it randomly. You can certainly like compute all of the gradients at once.
You have a question in the chat. Thank you for the nice talk. What is the difference between classical and quantum error corrections? Could you please explain the difference?
Well, I'm not sure I'm the right person to answer that question, but I can like share my view of it. So like for classical error correction, what you do is you use this like repetitions, right? You have, for example, one bit that could that is 0 if it's correct, and it's 1 if it's not correct. And then what you do is you can just replicate that bit for like 5 times. And even if one error has occurred, one bit has been incorrectly flipped, and then you can like still do a majority vote to like get the correct like bits. Yeah, and then for the quantum error detection, because there's like this no cloning theory, which you cannot really clone a quantum state without destroying the initial one. So you can't really do the exact same thing as a classical error correction. But then there are still like approaches like the surface code where you use multiple like qubits to create one logical qubit, which has much lower rates than the physical qubits that builds up the logical qubits. And then that's like the one way to do quantum error correction. And then so like the technique that I discussed in this lecture is not really quantum error detection, but rather like quantum error. It's not really quantum error correction, but really like quantum error detection, and then quantum error extrapolation. For the quantum error detection, it's more like you perform this like post selection. So you have done your measurements, and then you have some knowledge of how the measurement should look like, and then you post select. So you discard some measurements that are like unphysical, and then you keep those measurements that you think are physical. In this way, you can reduce the error. And I think in terms of the actual quantum error detection, error correction, like you build up a logical qubits with like a number of physical qubits. I think Nam did some of the work. If Nam is here to comment a bit on that.
What did you say after that? It's detection and extrapolation?
So it says that Nam may have more insights
Oh, okay.
in this than I'd have. Is Nam here?
Yeah, I'm here.
Pro
Yeah, my internet connection is not great, so I'll just briefly chime in about the original question about the classical error correction versus quantum error correction. So yes, there's certainly a lot of differences due to the inherent differences between classical and quantum mechanics. Yeah, including no cloning theorem, as Luding said. But the main idea is still the same in the sense that if you can somehow coordinate multiple qubits, like in a classical computation, you would coordinate multiple bits to encode one piece of information using multiple bits, and to encode in such a way that by the redundancy, you can detect if some kind of an error has occurred. You can do a similar thing with quantum bits as well. So you get a single piece of information, a single piece of quantum information. You encode that in a single quantum bit that's to do a quantum computation without the error correction. But if you start using multiple qubits to encode the single piece of quantum information across multiple qubits, by some kind of a redundancy that needs a lot more care than conventional computing due to the exoticness of the quantum over the classical, you can still correct some of the errors. So if you think about one of the very first quantum error correction code, like Shor code, essentially one uses 3 qubits to protect against a bit flip error. And then you use that as a unit of quantum information, and then you copy that 3 times, and then you protect against the phase error. So you, in total, expend 9 qubits to encode a single quantum bit of information. And so you have 9-to-1 ratio of a quantum error correction code. And so this is essentially one of the ways to use classical encoding scheme that is applicable for bit flip error. And then you concatenate that to protect against phase error, and then you can always come up with a working quantum error correction code. Although that would be, in a sense, very.
Simulator already has a pretty good accuracy. So would the reason for using quantum device with even doing error mitigation, is that because if the system size n increases, it takes too long to compute classically?
Right. So that's the whole point of doing a quantum computing, right? So quantum simulator is a classical. So the cost of performing the same algorithm on a quantum simulator compared to quantum computer, the quantum simulator will scales exponentially the cost for running that algorithm, so that we can only run like tens of qubits on quantum simulator for efficiently, I think. So if your system size becomes larger than that, then the cost of running the algorithm on a quantum simulator becomes so huge, and you cannot really do that. So that's why we need to use like an actual quantum computer, because it's quantum, not classical. So that's these could run in polynomial time. That we can like if it actually works, if we actually have like error mitigation techniques, so that we can reduce error to some low values, and then we have like thousands of logical qubits, we can actually run like the same algorithm that cannot be run on a classical simulator on a quantum computer. All right, so let's start from the first notebook 1. Okay, so in this notebook, we explore the performance of different optimizers for variational quantum eigensolver with and without noise. In this notebook, essentially, we'll be able to run a VQE algorithm on molecular hydrogen molecule H2 in a minimal basis. And once we set up our algorithm, we'll explore the performance of 3 different classical optimizers: the Cobila, the SPSA, and then the Adam optimizer. We'll also see how they perform if we add some amount of noise to the simulator. Okay, so we start from some setup, import IonQ and the Qiskit, and you add your IonQ API key to the IonQ provider, and then we import all the necessary thing like modules, Qiskit, and then Qiskit nature. And then let's first we need to define the unitary coupled clusters with singles and doubles ansatz. With a 2-electron 4-orbital problem, the UCCSD ansatz could be modeled by just a single parameter theta. And then this is our ansatz exponential I theta times this poly string. And then the next function is we need to form the electronic structure problem, obtaining the electronic Hamiltonian, and then transform it with a Jordan-Wigner transformation. And we also will diagonalize the Hamiltonian classically as a reference, as a like exact reference value. And then we like put things together. The overall circuit is constructed by first initializes in the Hartree-Fock state, and then applying the parameterized UCCSD circuits to it. And then finally, we define the classical optimizer. Here are 3 optimizers that use Cobila, SPSA, and Adam. And then we pass the parameterized circuits into the Qiskit VQE function, and then we set the initial values of the parameters to be 0. Okay, so let's first run the VQE optimization on the simulator using Cobila. And then if you run this, it will print out the circuit. It will print out the classical energy, the energy you obtain from the classical exact diagonalization, and it will also give you the optimized VQE energy. And you can see that it is basically the same as the classical results. And then we can plot the optimization process, and you can see that for Cobila, within like 10 iterations, the energy converges to the exact energy with some small fluctuations there. Okay, so that's for the Cobila optimizer. And then let's now change our optimizer to the SPSA and then see how it performs. All we need to do is to change the this parameter optimizer ID here from like Cobila to SPSA. And then once you run it, it will print out the classical exact results, the ansatz, and then the optimized VQE energy for SPSA. So it's here it seems that the SPSA is doing a bit worse than the Cobila. And then let's now like compare SPSA and Cobila for the in terms of the optimization process, and then compare that with the exact results. And you can see that so SPSA actually performed also quite well. It's the energy, the converged energy fluctuates around the this green line, which is the exact energy, but it seems to have like a larger error bar comparing to with Cobila. And then also you will find that SPSA certainly, in terms of number of iterations, it needs many more number of iterations to converge to the final results. So the last optimizer will be we'll try is the Atom optimizer. The Atom optimizer is a very popular optimizer in machine learning applications to train and used to train deep neural networks. So all we need to do is to change the optimizer ID to Atom. It will print out the classical results, the ansatz, and the optimized VQE energy. And you can see that the Atom optimizer works even worse. Now, if we plot the like the optimization process, you find that the Atom optimizer, shown by this green dot here, is clearly above the exact results. So the Atom optimizer does not work very well here. It converges to a much higher value than Cobila and SPSA. So far we've been running optimizations, the VQE optimizations on noise-free simulators. So quantum computers are inherently noisy for the near-term devices. So let's try to simulate an actual quantum computer. We'll do this by adding noise to the simulator and see how different optimizers perform under noise. We will add 0.5% of error for single qubit rotation gate, and we will add 5% of error for the CNOT 2 qubit gate. The way we do that is to import the Qiskit error noise model, and we add depolarizing errors to the single qubit gate rotation gate and the CNOT gate. And then with this, we can perform the VQE optimization using the same 3 optimizers, but now with noise. And then we'll print out the optimized result for these 3 optimizers. And then now let's plot the final results. And you can see that it seems that once we have noise, the Atom one still does not work very well. Well, the first thing we observe is that all of them are now like shifted up from the exact result because of the noise. And then the Atom one does not work very well. And now the SPSA and the Cobila seem to like perform similarly, and then the basically results in the like end up in the same point. Still, we see that the Cobila seems to do it with less number of iterations. Okay, so the last thing is that we can try the same thing on the actual IonQ's quantum computer, and then you can just try to write, because many like all of these 3 algorithms requires many like the SPSA and then the Atom requires like hundreds of iterations. Running these will take a very long time. So please be patient, and if you're not, you can try to like lower the maximum number of iterations required for Atom and the SPSA optimizer, and then like to get results sooner. Yeah, so in this notebook, we will explore the error detection techniques discussed in the lecture for VQE using the total particle number parity check. So you'll be able to run a VQE algorithm for the same like H2 molecule in the minimal basis. We'll implement an error detection approach that checks whether the total particle number parity is correct. Okay, so these stuff are basically the same as the other notebook. We define the UCCSD ansatz, and then we get the Hamiltonian. Oh, these are the same. Okay, and then this function, the error correction function, adds error detection to the VQE circuits. We do it by using this ancilla qubit, and then we add this ancilla qubit to our initial VQE circuits, and then we perform a CNOT gate to compute the like the total number parity. And then this function defines a pole selection process based on the measured parity. Essentially, what we do is we loop over all the measurements in the measured results, and if we check the parity, if the parity is correct, if the parity is actually 0, which is a correct parity, and then we keep these measurements, and if parity is wrong, we just ignore these measurements. And then instead of like computing the total energy, which is will be very complicated and will significantly increase the length of this notebook, we will compute only one specific term in the Hamiltonian. In this case, we choose a ZIII term. You can choose any term you want, but this is the term that I chose to compute. to demonstrate this error detection. And then this is the same as the other notebook. We construct the ansatz by initializing a Hartree-Fock state and apply the VQE circuits. And then this function defines, this function put all of these together and computes the expectation value of the ZII term and its statistical uncertainty. And then you see that it has an option of whether to perform error correction. And if if this option is true, we call the error correction function to perform the error correction, the error detection. And then now let's compute the expectation value of this term with no noise. And it will print out the circuits. It will print out the computed expectation value. And then in this case, the expectation value is essentially just 1. All right, so now let's add noise to the simulator by importing the Qiskit error model. And then now let's apply different amount of error rates and see how much error we introduce and how the error detection will perform to correct errors. We use 0% of error, which is noise free, 1%, 2%, 3%, 4%, 5% error for the 2-qubit CNOT gate. And then we use for the single qubit rotation error, we make it 10 times smaller than the 2-qubit CNOT gate error, which is a very reasonable approximation to the actual quantum device. You can see that it will print out the circuits. And one thing you will notice that for the error correction circuit, it has these additional CNOT operations controlled by these 4 system qubits, and then operated on the ancillary qubit to compute the actual parity. And then we can now plot the results, and you can see that this simple error correction. For example, one thing you can see is that the computed value degrades or deviates from the correct results as error goes up. Well, the error correction is capable of bringing this up a little bit. In this case, it's capable of correcting 50% of the total amount of error. And then we can run it on the IonQ hardware. This will take much shorter amount of time to run. And then you can run, if you run it, it will take some time. It will print out the circuits. Now let's directly go to the results. And then if you print out the results, you can see that without error correction, the computed value is actually pretty close to 1 compared to the noise-free one, which is 0.995, I think. This is 0.962. But with error correction, the compute expectation value actually becomes worse. It becomes 0.928. So this is actually very weird. So why adding error correction yields worse results? I initially thought this is because of bug, but actually not. So this is because the circuit that we're using is actually quite short, and then the IonQ hardware's error rate is actually pretty low. So even with non-error correction results, you can see that this result is actually very accurate, and the error detection itself, which include these 4 CNOT gates, these 4 CNOT gate is also noisy, so that the error correction circuit itself actually introduces more error than it could correct. So that's you see this counterintuitive results. So one homework you can do is try to use a longer circuit for VQE and see how error correction code there could help. And then one thing I need to say is actually this is one thing I said it's actually wrong. So here, what I showed, the 2-qubit gate error is from 0 to 5%, and the single qubit gate error is actually said to be the same as a 2-qubit gate error to demonstrate that the error correction code can correct this amount of errors. And then if we for example, if we change the single qubit error to be 10 times smaller than the 2-qubit error, and let's run the same thing. Now run, and then plot it. You can see that now we correct much less amount of error, because the 2-qubit the error correction circuit itself will introduce error, And now since the most of the errors is now in the 2-qubit gates, like we will we actually introduce more error than we can correct. So that's the amount of error corrected it actually becomes less. And then one thing you can try, and then the last thing we might want to try is to just change the 2-qubit gates error to 0. Let's see what will happen if we do that. So let's just multiply by the 2-qubit gate error by 0. And in this way, the error correcting, like error detection code itself will introduce no error. And the only error is from the single qubit gate. And then hopefully now the error correcting code will correct like the majority of the errors. Let's see if that's true. Hopefully that's true. Yeah, so now we can see that the plot shows that even with error rate as large as 5%, this error correction can basically give you this exact like the correct results, because now like the 2-qubit gates does not have any error there. Of course, this is not true in reality, but it does can give you some insight of how this error correction or error detection like algorithm works. All right, so that's it.
This method seems to work with the, I think, the errors that are in the basis, errors with respect to the basis of the parity check. If so, this method seems like a very simple method where we just simply not choose the basis states that we choose only the basis states that we know that should happen. Is my
Do you
thought
want me
correct?
to translate again? So what he's asking is like what we do in the notebook is we post select the some basis based on the parity check, and it seems like this like just make the circuit longer, and the like why we need to do the parity check in this case.
So why do you want to do the parity check if it makes the circuit longer? Is that?
So
I think
okay.
the go ahead.
So
it does make the circuit longer. That's for sure. In order to correct errors, you add more quantum operations here, and then but then still that doesn't mean that it's not going to be useful. In this case, because the shortage. What?
Yeah, but the question is actually, isn't this method equivalent to simply just selecting the measurement results that we know that it should happen? So
I see. Yeah, I see.
Okay. That's a very good question. So yeah, so if you just want to like compute, for example, for this particular circuits, you don't really need to. For this particular circuits, you don't really need to like compute the parity just using 4C0 gate. You can just like look at the final like measurement results, and then you can just human select, not by like this quantum selecting process, right? But however, the thing is that the reason for that is because we are computing this ZIII term, which is a classical term. And then if we want to compute some other terms, for example, like the non-diagonal term, like terms involving X or Y matrices, then we cannot really use this circuit anymore. We have to do some like orbital basis rotations after we do the like the VQE circuits to bring it to the diagonal, like bases. So once that happens, we cannot tell from like the measure results which is the correct parity, because we have provide some operations before we can tell like which state has a correct parity. Even states for example, if we have like a 0-1 state, which is like, for example, the correct parity, but then we perform some rotations with, for example, the Hartman gate, and then it could end up with both 0-1 and 1-1, 1-1 of state. And then in that case, we cannot tell whether like this incorrect of parity is because an error has happened or is because we have performed this basis rotation. So in that case, like the post-selecting by just looking at the measured results is not going to work. Does that make any sense?
I have a question about the computation speed. How much is it faster? I mean, how much is the quantum eigensolver, variation quantum eigensolver is faster than classical computer or the other method?
How much is faster? So the if you run like the variational quantum eigensolver, for example, using the UCCSD with a classical computer, you cannot really do that without exponential scaling, without exponential cost. So I think that the acceleration is exponential. So that because we can run like the UCCSD on quantum computer with polynomial time, and that is comparing with like the exponential amount of time for like a classical UCCSD simulation if you run them on simulator. So I think that the speed up is exponential.
Exponential to the number of atoms?
Is the number of electrons or the number the number of orbitals in the most rigorous way. Yeah.
I see. Thank you.
Seems like there's no more questions. So thank you.